Hi, everyone. Welcome back. My name is Martin Lovell. I'm still development manager of the Windows Runtime Experience team, just as I was when I was talking an hour and a half ago, unless I've lost my job in the interim. This is the Native Code 2012 panel, otherwise known as Huh? We're talking about what? And with me here, I have four people extremely more smart and experienced than I am, which leads me as the extremely strange moderator of a panel much smarter than myself. We're going to start by having everyone on the panel introduce themselves and talk a little bit about who they are and how they're still ending up on a native code-based panel in 2012. And after that, we'll take questions and answers from the audience, and maybe I'll interject some questions I got via Twitter and Facebook and other questions coming in. No, I'm just making that up. If there's no questions, I'll make up questions and pretend they came from Twitter. Okay, first, Walter Bright, why don't you introduce yourself?
I'm Walter Bright. My experience with compilers is I've written a C compiler, a C++ compiler, a Java compiler, a JavaScript compiler, and currently working on D compiler for the D programming language. And I'm into native code because, well, you know, I just like it better than bytecode. And I feel comfortable knowing my program all the way down to the bottom. Never felt comfortable handing it off to somebody else's VM to execute. So I like native code because it's fast, it's efficient, and I can completely control it as a programmer.
Robert? I'm Robert. Is it on? I'm Robert Griesemer. I helped design the Go language. Before that, I had the pleasure to work on the V8 code generation, and a little bit before that on a DSL that was used internally at Google called Sawzall for log data processing. In a lifetime completely before that, I worked on the JVM, the Java Hotspot JVM, and even before that on a language called Strongtalk. And why do I like native code? Well, there's a certain thrill that comes with driving fast cars, especially if they're safe. And I think that's it. Oh, and I should introduce Gordon, the mascot, the gopher, the Go Gopher. So, you know, given out as a prize for the best question, I guess.
I'm Andrei Alexandrescu. A bit of an imposter here. I'm seeing people in the audience who should be here much more than I should. 11 years ago, I wrote a book, A Modern C++ Design, which became, like Q-tips became a common noun, like everybody says, oh, I'm writing modern C++. I'm an alumnus of University of Washington across the pond, computer machine learning, and I also helped Walter with designing the D programming language, about which both of us are going to talk tomorrow. And essentially, I think getting into the purpose of this panel, I think things are a bit misunderstood or misspoken, because I don't think native code should be an end goal as much as one of the available code generation mechanisms. So just like there's this great talk by Andrew yesterday about Haskell, a company using Haskell for example, natural language processing. They could use anything they wanted. They chose to use Haskell because it offers certain advantages. But if Perl would have been better for specific tasks, such as, I don't know, stemming, I don't see any reason for which they wouldn't want to use Perl or Python or whatnot for specific subtasks. Similarly, I think that native code generation is not an end in and of itself, as much as a mechanism that, yes, we want to use if advantageous. Otherwise, we don't want to use any other available mechanism.
And I'm Herb Sutter. I've done a little bit of C++ in my career, and I currently run the ISO C++ Standards Committee, a committee of volunteers who puts up with me doing administrivia. And also I lead the C++ language extensions design team here in Visual C++ within Microsoft. And I have a curious relationship with Walter Bright, who I've known for many years before he ever had heard of me or I of him professionally in language design, because you made me waste way, way too many hours with Empire. Thank you for Empire.
I've destroyed marriages, careers, everything with Empire.
And my relation, Empire is, think Civilization Light. Like, great and in text mode. And my relationship with native code goes back to even further than Empire. And I'm a big fan of using the right tool for the right job and not trying to pretend one can and should do everything, including native code.
And to finish out the introductions, I've been at Microsoft about 16 years, but it turns out that the very first time I wrote any C code at all was on Walter's compiler, the then called Zorland C, a name which for some reason got quickly changed. And I was in high school, and my friend had an IBM PC, and we had Macs in our computer room, but we didn't have Think C yet. So I was on Zorland C for a little while.
Is that Zortec or Zorland?
Zorland. It became Zortec later. And then I came to Microsoft. I work in developer division on tools, on debuggers, IDEs. Eventually ended up on the C++ team working on libraries and on the extremely complicated and difficult marriage of trying to bring C++ to .NET. And then more recently, I moved to Windows and started this thing called Windows Runtime that those of you who are watching now already know about, but for the people on the video, Windows Runtime brings the Windows platform to languages of various kinds. And one of my passions here that we've managed to deliver was to bring the Windows runtime of the Windows platform to a dynamic language like JavaScript, to a managed language like C# or VB, and to a native language like C++, and have all of those be first-class citizens and each language be able to participate in a natural and familiar way. So I'm very excited about native code, not in the sense that I expect everything to be native, but I'm very excited to have brought it back to a world where native is a first-class citizen right along with managed, right along with dynamic, and right along with script. So that's super exciting for me. Okay, so the theoretical structure of this panel is that you have questions for people about native code or other similar topics, and we have answers. The alternative structure is I have questions and they have answers if you don't have questions, but I'm betting there are some questions in the audience. So who has a question for the native panel? Nobody?
Option number 3 is that we all have 4 talks tomorrow and we can get beer.
Yes. Okay, I'll start priming the question pump while you think of your really great questions. So let me ask this. It's 2012. There are plenty of managed languages out there, but each of you represents a technology that's moving forward aggressively and interestingly in the native space. Tell me what you think the biggest plus points you get out of being native are, and what the biggest negatives you get out of being native are.
Okay, biggest plus points. One is you can directly call C code from it. Because C is native, you don't have to go through any sort of translation layer. The entire C universe is, literally one CPU instruction away, and you've got it. By generating native code, I like to be able to control exactly what the code is on my users' machines. I'm not dependent on the user calling me up and said, hey, it happens to run slowly on my machine because maybe I've got there's a poor VM implementation on that machine. I don't have that problem. I can optimize it, and I can know the code is good that's going out to him. I can control exactly what it is. I'm not dependent on a tool that I may not even have a copy of to execute my code. So essentially, I can control the user experience right down to the bottom with native, and that's important for me as for quality control of what's happening.
Yeah, I would say that the main advantage is speed. Of course, you really get you're as close to the metal as you can get, and you can do whatever you want, and you're not bound by any constraints that some virtual machine is giving you, and that's probably like an impedance mismatch between your language and what you really want to implement. And there's another thing actually which is perhaps surprising. The VM, if you will, that the native machine provides you is surprisingly well spec'd out. And it's actually tested and usually works because nothing will work otherwise, which is not necessarily true for other VMs. So it's kind of nice.
So I mentioned a bit my view already. I think that the largest advantage of native code is today still remains speed and control. And the largest potential advantage of, and consequent liability of native code, the largest advantage of managed code is the ability to do advanced processing during load time in the form of just-in-time compilation, specialization, special casing, hotspot identification and exploitation, and such. Such techniques are not unavailable to native code, but traditionally they're just not. People don't do that. In a way, managed languages are forced to do that for efficiency reasons, so as to recoup some of the impedance, that mismatch that's being created by using an extra layer on top of the machine. But I'm not sure 2012 is the year. The world is going to end, so probably this is it.
Actually, it turns out we've leaked an ad ref on the world, so it's not going to end after all.
We got an ad ref in tow there, perfect. And it's atomic too, nuclear. Okay, I think, I'm not sure 2012 is the year, but I think the future is still has a few potential surprises in the mix in the form of advanced just-in-time compilation techniques that could actually, at least in theory today, bypass the performance of statically compiled code. Again, that's not to say that such techniques are unavailable to native code. It's just that they're much less usual and much less explored within that space. However, to sort of make a point that's an umbrella over both, it might as well be the case that this trend of managed languages and VMs is motivated by the momentum that's now just about to fizz out of increased serial performance of computation. So there's been a lot of for long period, many years, decades. There's been this phenomenon of growth of and scaling up of speed, of serial speed in the form of the frequency Moore law, so to say. So, and then people started to be more wasteful in a way by creating additional abstraction layers and additional, affording themselves to lose more speed in the form of interpreted languages, in the form of dynamism, in the form of managed languages, bytecode, etc. And now the question is, this is a sort of a race of arms, because what if this whole trend is fizzing out? There's no more scaling in serial speed, and all of a sudden it becomes much more interesting to actually watch closely for serial performance, because you can prioritize only this much, and at the end of the day, there's going to be some serial execution that's going to happen there. And you want to make it as fast as possible, because taking a vacation, taking a sabbatical is no longer an option for accelerating your program. So it's going to be really interesting what's going to happen. So I'm not going to emit any judgment at this point. I think the advantages and liabilities of both systems, and I think the future is going to be very interesting.
You're tempting me to give half of my talk tomorrow now, because actually a very large part of it is how does native fit with managed in particular, as well as dynamic and script and other kinds of languages, functional. So I'm going to try very much to resist that temptation. But I said at the beginning, it's very important to use the right tool for the right job. You are not going to get very far by selling as a hammer as Screwdriver version 2 and saying, well, of course you should just use it. It's just better at everything. That's fanboyism. That's not really a rational assessment of a particular tool's strengths and weaknesses. And native code and managed code, well, first of all, we should define what native code means, because I will bet you it means something slightly different to everybody here. But in general, I would define native code as a language designed, a native code language, as designed to prioritize performance and control. So it's not just performance efficiency, compile time, and that kind of thing, and the execution time, but it's also control over layout and determinism and ordering. Prioritizing those things over everything else, including programmer productivity, if they are intention. C++ will never give you a productivity feature at the expense of unavoidable performance overhead on code that doesn't use it. Managed languages do exactly the opposite. When there is a tension between programmer productivity in and to enable a certain class of programming, especially for mainstream general purpose language programming. If there is some overhead that we can pay, even if it incurs a cost on programs that don't use it, but it will make users' lives considerably easier, managed languages generally pay for that kind of thing. They are willing to do that. So that's really the difference, which means that a well-designed managed language and a well-designed native language, because there are not well-designed ones, but let's talk about the well-designed ones, are aware of this trade-off either instinctively or explicitly, and they are crafted tools for a particular job. And then you get to choose what your problem is. If your biggest cost for your application or for one part of it is programmer productivity, choose a managed language for that part of your application or for that application, because that's what managed language is optimized for. And if you can tolerate the overheads, which when we have a surfeit of compute cycles, often you can. If your biggest cost is not programmer time, if it is performance per transistor, performance per watt, performance per dollar, then use a native language. This can be different parts of the same application, but use the right tool for the job. And it's a mistake, and people do it all the time in both directions, to pretend that one tool can subsume the other. It's just not true. It's not what they're designed for, and it's not fair to either tool. So it's a universe where we want to use both together for different parts of the same problem, often in the same application.
I'm going to add my comments on native, and then I'll take Brad's question. As you know, I work on the Windows team, and the Windows code base consists of, these days, a little bit of assembly language, quite a lot of C code, a large amount of C++ code, and a decent amount of C# code as well, plus a little of VB. So we have a lot of code of different kinds, and when you look at it for real, there's also a bunch of script code, Python, Perl, other things bouncing around, and even some JavaScript. So we have a lot of different kinds of code. And we do try and choose the right tool for the job. And we also try and stay compatible with ourselves from a long time ago. So we rarely take a piece we wrote 15 years ago and rewrite it in a different language and get that direct experience. But we are seeing a wave of hardware that's changing everyone's expectations. Andre mentioned the end of constant compute cycle growth. But even before we hit that particular milestone, I bet you most people in this room have a smartphone, and it's smaller, a lot smaller than their desktop PC. And many of you may have bought one of those pad things that I think some other company is selling, I'm not quite sure, that is also a smaller, less fast machine than what you have on your desktop. And we're seeing the rise of these very mobile, very attractive, very, very responsive machines, but they don't have the hardware profile of my quad-core 8-meg desktop machine I bought 2 years ago. They're really smaller machines, and we have found that for a lot of the core pieces of Windows, to make them fast enough, to make them effective enough, native code is the only way we can get there using today's generations of tools. And so, again, we use managed codes in places, we use other kinds of code in places, and the Windows runtime allows you to use any kind of code to build whatever app works the way you want it to work. But there's a set of uses that we find native code essential for to get the kind of performance we're looking for. And that's really what draws us back to native more than anything else, is that we think hardware is not necessarily getting bigger for a while. Instead of having a bigger PC, you'll have a more mobile PC or a PC with better battery life. In a lot of cases, a more desirable choice for our customers is a PC that will last for 2 weeks sitting around doing nothing and just syncing your email than a PC that weighs twice as much, or a PC that has other features. And so the trade-offs being made by customers are very different from the trade-offs being made 5-10 years ago, and we have to respond to that in the software, and that's, I think, the biggest reason why native is seeing a renaissance. Brad, let me bring the microphone.
So, to Walter, my first PC compiler was the old Datalite C compiler, and I paid the extra $49 to get the source code to the runtime. So. But particularly on the old PCs, they really illustrate the problem for native languages that I hope the next crop of native languages don't repeat. And that's providing interoperability at a calling site. You know, the whole DOS Windows platform really never developed a common calling standard for native languages. If you recall how hard it was to call from Pascal to C to pretty much any other language. So unless there's someone really driving a standard for interoperability, I think you're going to have some difficulty on that.
I'm not sure what the question is there, but there are many different calling conventions. I don't know. I've never tried it. And I don't know what ABI...
If they both use the Windows runtime, they can. Ta-da!
Well, I'd best let him answer that because the D language follows the native C ABI on the platform. And so on Linux, all the different compilers or languages seem to use the native C ABI if they are native compilers. So they're all pretty much interoperable.
I actually think this is not a question about native languages versus, let's say, non-managed languages or anything. It has something to do with the execution model that the languages are dealing with. And if you have a language that is garbage collected, and you have another one that is not garbage collected, and the one that's garbage collected uses an accurate garbage collector which moves stuff around, you're going to have like serious issues at the border when you go between those languages. And another thing is if you have one language that has one threading model and another language that uses a much better threading model because it's more lightweight or different or whatever, you will have an even worse problem at that point. So this is not I think this is nothing to do with native languages, really. Now, I'm encouraging interoperability, but I don't think it is a fault of the native language per se. It's
Well, a lot of
language design point of view, it's not. It's an implementation issue for sure on the Windows platform. And as we're getting more and more interested in native code, that could be a problem that could be interesting to solve. As Martin says, he has a solution for that if you're willing to pay that overhead and talking to Windows anyway, right? So, however, it's not a language design affecting issue as much, unless you consider DeclSpec part of the language.
Well, it could be that, C is the lingua franca, okay? And most languages seem to construct themselves a way to call C functions. So if your language can call C functions, theoretically they can call any other language that calls C functions.
JavaScript is the lingua franca at this point, I think.
Not PHP.
So one thing I noticed is I think this is a real problem, and one trend I noticed for companies that do this sort of high frequency, high bandwidth, high traffic computation, such as Google or Facebook, they develop protocols for interoperability that are sort of language. Let's say not agnostic as much as they remove themselves from any particular language and provide bindings for each. Google has protocol buffers. Facebook has the much better Thrift, Apache Thrift, and both of these layers actually allow a small meta language to specify interfaces. Thrift also has exceptions, data types, structures, maps, arrays, lists, and whatnot. So just a small amount of basic data types, and they do so on the Windows platform. We're seeing the resurgence of COM from the dead, which makes me very happy because you know what, I love addref and release just as much, and. So I'm seeing which actually COM is actually on the common interface that anybody can plug into and use at a relatively small cost in representation. So I think that is a problem. I don't think it's as large and as unsolved a problem as it might be seen as.
Now, I have a question for Andre, since you know a little bit about Facebook. So to the extent that you can say this, my understanding is that things started off more in the PHP, Java world in the Facebook implementation. And I understand that there's a lot of C++ being done. But why? You've got lots of servers. What's a few more?
Well, so for any questions about Facebook, press@fb.com. So actually, it's an interesting point. So when I joined Facebook 2 years ago, there are much more many. I was a rarity. Like, oh, they hired the C++ guy. So interesting. So I was a sort of a rare guy. Let's say probably 10% of the workforce was doing C++ backend code as opposed to PHP. And over these 2 years, not because of me, of course, but as a general change of wind in the sails, so to say, Facebook has hired a lot of back-end engineers, an awful lot. And right now, I would say probably they're almost on a par, C++ and PHP developers, front-end and back-end. So a lot of the Facebook's back-end is written in C++. And it's very good. It's just good business. Facebook consumes very little, literally very little watts. I can't say the number, but very little watts per user. Actually, fractions of watt. Not to get too much into details. Very little, power per user, per active user at any given time, and that is because of a concerted effort of offering as many features as possible within a confined computational real estate. And essentially what happens is everything that's back-end, high-performance ads is C++ because it must be responsive and well done. And even our PHP compiler translates statically into C++, and then the C++ code is compiled. It has 30,000 global variables. I'm not kidding, actually. We found a bug in GCC, which is like, you use a singly linked list for all globals, so that's awfully slow. And they're like, you're the only idiots who have like 30,000 globals. So essentially, we compile statically, so actually Facebook is quite literally running on C++. We also have a JIT for PHP that's obviously written in C++ and generates machine code during runtime, which is sort of we're aiming to make it almost as fast as the static compiler, but there's a lot of work to be still done. I'm sorry, am I bloating myself too much? So in essence, using in Facebook's case, very concrete today, using a native language such as C++ means more features for the same power and less power for a given set of features. It's a very simple equation.
And there are two things that struck me out of that, because I did not hear that full answer before. So two new things that struck me. One I kind of expected, which was you mentioned time to solution. Making queries happen faster. Yep. Now you might think, well, we're distributed, we're parallel, we should just run more things because that you'll get much better scalability that way, and that's true too. But however wide you scale, if you also bring it in this way, you'll get the same X performance. The other thing was you said something that was really profound, and I don't know if everybody caught it, and the people in the room might catch it, but I want to make sure people in the world get it. Our measures, our metrics are changing. You said power per user. When have we ever measured in the enterprise mainstream applications based on power consumed per user? That is going to be the norm. And that and other performance and cost per user, per computation, is going to be the norm for many classes of applications for the rest of our careers.
Looks like it, yeah. Bart.
Next question here. So many of you mentioned the efficiency of the code that you generate, but none of you mentioned the efficiency of data structures that you build in these languages. And actually, that is a big problem at big scales because garbage collecting large heaps takes a lot of time, but it's not just the garbage collectors, that the fixed cost of a VM in terms of all the meta representation of the classes and all the extra stuff that you have, and you have so much more control with the native language. So none of you use that argument, but you should.
I said it. I said because everybody was talking about performance and JIT and such, and I said and control. Martin, and which includes especially object and memory layout control, as well as determinism and ordering, were the other things I mentioned. But layout and control, let's talk about that. Modern processors love arrays. You can't beat the per element overhead, which makes it fit in cache, but that's a small thing. That's such a 1980s thing to be thinking about, 1990s maybe. But access order, if you're going to traverse the whole container, never mind that it fits in a smaller amount of cache, but especially if you do more than one traversal, but if you access things in exactly memory order, increasing or decreasing, what kicks in? Prefetcher. That's roughly order of magnitude performance increase on memory right there. You cannot get that in a pointer chasing node-based language. Or sorry, I shouldn't say language because that's pejorative. You can't get in a pointer node-based pointer chasing data structure, which it is difficult to escape from in certain frameworks and languages. You can work against the environment to get that, but you are doing that. You are saying, I'm going to work hard to get my array back so I can get that performance. So that's just an example of what you're talking about. As there are many classes of performance where we say, hey, in the name of programmer productivity, if that's your biggest cost, give some of that up, then that's a perfectly legitimate design point. But it's not the only interesting design point. It can also be very interesting to put the focus the other way. And I'll make the case tomorrow that they are not in tension most of the time, actually, those two things.
Well, I'd like to amplify on that. There's also the layout of your code. It turns out that the way an operating system runs your program is it doesn't load it into memory. It just simply, it does memory mapped I/O. It just maps your executable onto memory, and then when you jump to an address in it, then the operating system goes and loads that page into actual memory. So you can have a very large program that is compiled native, and if you're only using a very small part of it, actually only a small part of it sits in memory, and the rest never gets off of the disk into memory. And you can exploit that by putting code that calls each other next to each other in memory, and code that is rarely used, you can put grouped together in other sections, and those rarely used codes may never get loaded into memory. So you can get startlingly fast program load times, even for giant programs out of this, if you order things carefully. It's also true that the operating system will speculatively load things in increasing address, thinking, well, if he's executing this page here, he's probably going to start executing the next page soon, so I'll preload it. I don't know for a fact this does it. It's just sort of empirically by testing. If you run your code forward, it runs faster than if you run your code backwards. So if you organize your stuff so your normal flow of control is forward through your code, it will actually load faster. And this idea seems to get forgotten and rediscovered about every 5 years. But if you're writing code targeting a VM, you have absolutely no control over the layout of the code. Not only that, is because it's a VM, it's not statically compiled sitting on the disk, and if you don't use it, you don't load it. No, it's got to load the whole thing.
I have to throw a wrench into this because I used to work on VMs. So,
okay.
Some of the code that gets executed dynamically, and so the order of the execution is depending on the data. And so VMs can actually do an excellent job in, ordering the code exactly as it needs to be for your particular data set, which might be harder in a statically or natively compiled fixed,
But it does that at runtime, right?
It does it at runtime, but if that data, happens, or if you have significant amounts of data, it can potentially beat this. I'm not saying, I'm just saying there's two sides to the sword.
Okay.
Now, I have lived that discussion in public over the last 24 hours since about midnight when I foolishly blogged a comment about JIT compilers. And of course, all
already destroyed.
Yeah, and all the antibodies came out, and of course they were wrong, and I was right because that's just the way things are. But seriously, I think there is an important point there. JIT compilers can do magical things. They have, for one thing, they have more information. Therefore, you can do more. Okay, you know more about the runtime environment. Having said that, that's not a unique advantage that applies only to those languages and compilers. The way I like to characterize it is it's prevention versus cure. And it's perfectly valid to optimize for something other than performance, right? But let's say we do that. Say you design a generic system, unlike C++, where templates are not just static calls, but inline by default, like just the screaming fast, the inline by default. You don't have to do anything. It's just the way it comes out of the box, versus say .NET and Java generics, which are all about virtual dispatch. Absolutely, you can be really smart and create really robust and complicated and smart tools to de-virtualize and figure out your call patterns and inline it anyway, but that's cure, not prevention, right? So the point I would make is, and that's one of several examples you can say where managed languages opt for, let's deliberately give up performance because that's a good trade-off if you're deliberately designing for productivity. Let's give up some performance and bet we can make most of it back through tools, through cure, whereas C++ and native languages tend to go for the prevention. The observation I would make is that if you go for prevention first, you can also always add the cure too. If you go for the cure first, it's too late to go back to prevention. Once the genie's out of the bottle, it is always harder to undo something than to not have made the mistake in the first place. I come from the database field back in the 90s, and we did distributed databases. And a short anecdote there, it is perfectly valid in the web world, believe it or not, to not have consistent databases, to let databases get out of sync. And sometimes we do that on purpose. And you're losing the C in ACID, which is really scary. It was really scary for a lot of people, still kind of is and kind of should be. But if you want to keep databases consistent, you are always, virtually always, much better off doing lots of extra work up front to keep them consistent. Even though it may kill scalability, it may kill some overheads, it make you run slower, you need bigger hardware. Because if you let them get out of sync, it either A, will likely take even more effort later to get back to consistency, or you may never get it back again. It is much hard, if you're going to do compensating rights and those kinds of things, it is much harder to go back, to get back what you lost, than to simply refuse to give it up in the first place. And so this prevention cure thing, when you talk about heroic efforts of, say, JIT compilers and that kind of thing, you can always do that cure on top of prevention. You could not, once you opt for relying on the cure, go back and try to get the prevention too, because it's too late. You've already given that up and you're trying to make it back.
Yeah, but the counterpoint here would be that cure and prevention may actually swap because, for example, a VM may enjoy some security properties, some safety properties, and those are prevention. So you have that, and then you have unsafe C code, and you want to bring a safety back into it. And there are people here who have done work on that quite literally. So cure and prevention may actually be exactly the exact opposite. Shaz?
But you're talking about different things, right? I was
Yeah,
talking
exactly.
About, so you may in fact make a completely sane and legitimate language design decision or system design engineering decision to opt for I'll give up default performance loss prevention and rely on cure to get it back because I'm going to prevent security problems. Right. So you're trading off one prevention for another, say, I'll cure that one and prevent that one. And that's a perfectly legitimate trade-off. So is the opposite.
Yep. And
Can I take the next question?
I think Shaz, he has a topical point to make.
You have a point on topic? I have a question also. I have a question here, and then over there.
Right. Well, it looks like you are preaching to the choir here. It's like all these programmers here are native programmers, probably.
Actually,
right?
can I ask that? Because this is the very first time this conference, which is called Lang.net, Next, for the first time this year, it got that little X. So we're here for the first time. Thanks for inviting us. It's great. Native code and native languages. How many of you are native programmers or language designers?
That's maybe
okay. The longer you wait, the more hands come up. It's all right. And how many are managed programming language designers?
Maybe two-thirds, three-quarters?
Yeah, about 3 to 1 managed.
Both. Oh, that's pretty good.
So there's choir, there's unwashed masses, and there's both. All right.
It's maybe a third.
We'll talk more tomorrow. I'm sure there'll be questions.
No, so that was just an introduction to. I always like to be a devil's advocate, so I'll now say a controversial thing is that this is the end of native programming, and the argument is that native programming is you know about your target upfront, right? You know what processor you will be running on in particular, right? Now, where the industry is going is, first of all, going multi-core, going GPU, going distributed. This is, so your program will run in the environment that you cannot predict. Like in the old times where you would be running on a single x86 processor, you knew everything about it, so you could apply maximum optimization upfront. But in the future, or actually even now, you don't know what platform you'll be running on.
I think
actually
that's not true. I mean,
No.
how many processors are out there that are actually being used very frequently now? It's x86 and there's ARM and there's maybe
it.
MIPS in embedded space.
I'll
That's
debate
it.
that there's
Okay.
MIPS.
But that's just 3.
I mean, we're down.
There's
Actually, if you look
way
10 years
fewer
ago-
than 10 years ago.
10 years ago, you had a dozen major
Okay, but-
architectures. Now we're
but
down to
you
2,
needed
so
a
it's actually gone the other way.
compiler for each processor,
Yeah,
right?
I don't see trouble with that.
And now you don't even know how many cores will be in your
Well, that's
in your
right.
computer,
But you
right?
write your code to be agnostic to the number of cores. You express the parallelism and let the runtime spread that across whatever
The
number of cores
runtime.
are done.
So-
right.
so
no, but not.
What's the
but
difference between the runtime and the interpreter?
It's very different. Remember when you wrote your 1970s C code? Somebody asked me this in Kansas City a couple of weeks ago, so I'll just repeat the answer here because it's a really good question. I'm glad you asked it. You write your C code, you compile it to whatever your instruction set is. And then how do you run it? On even a plain old Unicore machine. The OS schedules it dynamically. That's all we're doing. You do the code gen, and you emit, x86 and say ARM if you really want a fat binary that can run on both. I can spread that on 100,000, 100 million combinations of cores, that some of which are x86, some of which are ARM. Easy. In fact, the heterogeneity is much less than it was 10 years ago because the industry is coalescing in particular around x86 and ARM. Now, where there is going to be some increase in heterogeneity is where specialized cores are coming in. GPU, the cell-style SPUs, those kinds of things. Right. But it still won't be as much as it was even 10 years ago, I don't think.
I'd also like to add that one of the problems was once you try to move your project to another compiler, another processor, it wouldn't compile anymore, or it would compile and not work right anymore. I think there's been a lot of progress in making languages more portable and compilers more standard compliant. So that's much less of a problem than it used to be.
Next question is over. We got a guy over here.
So earlier you described a continuum between languages that let you have control over representation versus programmer productivity. I'd argue that it's more of a triangle where you have this axis, and then there's also the axis of wanting to optimize for language simplicity. So I think you can have control over representation and productivity, but you have to give up simplicity and you get C++, for example. So not that that's a bad thing. So when you're designing, the respective languages you work on, how do you determine how to optimize for all of those axes simultaneously? Like, how do you determine what your complexity budget is?
Let me give my answer tomorrow in my talk. But.
Same here, actually. Going to destroy tomorrow, so be here tomorrow, okay?
I probably have to say the same.
That question they're not going to talk about tomorrow.
I'll answer. It's like art. You have to look at each thing, and one of the most difficult decisions you make as a language designer is what is worth putting in the language and what should not be in the language. And you have all these criteria and all these principles you espouse that turn out to be contradictory. And in the end, it comes down to something what Andre called good taste. I mean, does it look good? Does it feel right? Does it have that feeling like it belongs in the language? And I don't think that you can reduce that to a set of principles.
Now, having said that, taste and elegance is so important. So anytime that you're designing a language or anything, it's never just two things. That's an oversimplification. These are just two major things that show the difference between native and managed priorities, that's all. But here's a homework question for all of you. And for those of you who are online but haven't watched some of the talks that are going to happen in our future tomorrow yet. Homework question. Which is the most complex modern mainstream language in terms of the complexity of its language specification, just the language? Language specification, is it well, somebody already yelled C++, so let me finish the question. Is it C++, C#, Java, and support your answer? You will need to do homework. You do not know the answer.
I'd like to amplify that a little more. Has anybody designed a house here, or an airplane, or a car, or something like that?
Operating system.
Operating system. What you find out is everything about that is a compromise among competing things. Like, do I want to make the closet larger? Well, then I have to make the bathroom smaller. Or it's going to increase my cost, or it's going to take longer to to construct or something, everything is a compromise. There are no hard and fast rules, except it has to pass the, the building inspector.
You read
This
Fred
reminds
Brooks'
me-
latest book, didn't you?
Sorry.
Fred
No, I
Brooks'
haven't.
latest book? Oh, he like.
What was that question?
Hot mic.
Run, don't walk to read Fred Brooks' latest book, which I think now is a year or two old. It's not the Mythical Man Month. It's a sequel on design. The Design to Design. Thank you.
Was #1 on Amazon.
It's great, and probably at Facebook.
This reminds me of, I saw an ad on TV recently for something. I don't remember what it was. And the slogan was, engineering without compromise, which clearly seems like an oxymoron to me.
10 minutes.
You had a question.
Thanks. So I used to program in C earlier, and then I started programming in C#, and I found that to be a very pleasant transition. And the most pleasant aspect of it was, I think, the memory safety and the garbage collection. Now, it would be really nice if all the control that you guys are talking about that you get with languages like C and C++ could somehow be married harmoniously with memory safety, right? It will make programming much more pleasant. So what's the latest word on that?
Go.
Go. So you're talking about that tomorrow?
So, actually, so the current technology still puts a natural tension between safety and efficiency. So unfortunately, this is here to stay. I think one obvious pain point is there's garbage collection. So today we don't know how to make safe programs that are non-trivial without some form of collecting garbage. We don't know how to free pointers and prove that they're not used anymore, ever. And second would be bounce checking, which is theoretically very well understood, and it's the techniques for systematically eliminating unnecessary bounce checks are well known. However, it's a hard problem. It doesn't scale to large programs. Such analyzers don't scale well to large programs. And essentially, it's a thing. We know how to do it theoretically. We cannot really do it in practice. So array bounce checking is one of those things that are, again, understood but difficult to implement efficiently on large programs. And garbage collection, I don't think we have a very good, as a community, I don't think we have a very good attack on this issue. Dan Grossman, who's here, designed Cyclone, which is a C-style language that actually tracks ownership relationships and is able to prove things about programs saliently. But Cyclone turns out to be quite difficult to use in practice because it requires a lot of annotation from its users. So, I'm confident that there's going to be progress in the area. I don't think we're close at all to the last word in the matter.
So I want to take out garbage collection, not because I think it's easier or not, solved. It's not, but I don't think it has something to do with it. It's orthogonal to the fact whether something is a managed language or a native language.
Oh yeah. This is what sort of transgresses, and my whole point was that there's still tension there, and we're working on this. We have our best people working on this, and the last word is out there, probably in the future sometime.
So it seems sometimes if we compare managed to native, it's like comparing like hand-optimized assembler versus like Smalltalk. Like, is there some continuum in between those? Like, for example, adding GC to C++, for example, or some other things where like JIT compilation might be not, something you want to pursue or reflection, but there are some features in between where you could envision like a language that is designed such that you can add, features in the language, like a layer cake, and you basically make your own decision, like how much you want to sacrifice in performance versus productivity. Is there any, ideas in that direction?
I mean, somebody said at some point that every sufficiently large C program has a Lisp interpreter built in somewhere, and I think that's true. You know, as soon as your program is sufficiently large, you do some kind of memory management yourself, and it's very likely that if you're not very careful, it may be much worse than what could be done automatically. And then, secondly, there is of course all these, there's libraries that you can add to C code, for instance, to get garbage collection. It's conservative, but you can do that. And there's garbage collected languages like Go, which if you don't use allocation, you have very good control over what happens, and you don't necessarily invoke the garbage collector where you don't want to.
I think just a sec. I think we're trying to say a very strong word with D in this very particular matter. The way we've designed D is to have a provably safe subset that is entirely eminently usable. You can write entire applications in the safe subset. And there's user-defined control. You can annotate code with this is safe, this is trusted, this is system. So there's sort of three realms, three universes that can interact in well-defined ways. And as long as your whole program is tagged as safe, you can actually prove that your program is memory safe, does appropriate bounds checking. There's no leaks. There's leaks could be, as in any garbage collector program. There's no dangling pointers and such. And then inevitably there's going to be a small part of your large program which is going to be trusted, meaning I check it by hand. The compiler is unable to, the language is unable to prove that this code is safe, but I'm going to give my word for it, and I mark that code as trusted. And finally, there's system code that neither I or the compiler can prove anything about. So I think we are on the way to making a very strong statement in exactly this area with a language that has a usable, because C++ also has a safe subset. It's just not usable because you can't do anything without pointers in C++. And the minute you have the femtosecond you have a pointer, you're unsafe. So a usable subset that's provably safe. We need to do the actual proofs formally. And then you have, on top of that, you have a trusted layer, and then you have a system layer. So, we can discuss more offline about that.
It is true that C++ has a type-safe and memory-safe subset, and in particular with standard smart pointers now. You can
if you
use
include the library, the
code.
discussion changes quite a bit.
Yes. And I mention that only because the story in C++ always was, just use reference count and smart pointers, roll your own because there aren't any good ones in the standard. And so it's actually important that as of last year, there now are. So you can actually write portable code that is type safe and memory safe for the first time in C++. Yes, and you need weak pointers, and yes, there are cycles, but that's reference counting is the first form of garbage collection.
I believe it is memory safe, but the compiler still doesn't prove it.
Right.
Or not that that's impossible that it could, but I don't know of any that does.
Sometimes it's great to build programs that are safe by construction.
Okay, time for one last question.
Sorry to beat a dead horse, and I understand that this is a language conference, but one of the questions prior about whether or not it actually is possible to consider the distinction between native and managed code. I noticed that the phrase that was being used by the panel was native languages versus managed languages. And I'm wondering, with things like Google's native client, which doesn't seem to have gone too far in the marketplace, but something on the server side that's very popular is virtualization. If you're using what would probably be considered to be a native language to target a virtual machine, is that still native code? If that virtual machine is executing in an environment that is not actually reflected by inside the walls of the virtual machine. And how does that influence your decision? Would that be something that perhaps you would not consider to be a native environment anymore? Would that be repulsive to you, or perhaps insulate you from the inevitability of managed code, which I'm not personally convinced is the case, but some other people might be?
I guess I can answer that. If you program in the safe subset of D, you could run it under a VM.
Yeah, absolutely.
Absolutely.
But I think the question was a bit different. It was about virtual machine monitors, right? Like VirtualBox and VMware. All right. Yeah, essentially, I mean, one thing that should be understood is that VMMs actually run native code at full speed for the most part, except for device driver interactions and networking and such. So I don't think they add any dimension to the problem we're talking about here.
Another example of that is that Visual C++ for 7 years now, since 2005, if you compile any portable standard ISO-conforming C++ code with /CLR, we will, instead of generating x86 instructions, or now ARM instructions, we would generate .NET-IL instead. That is a native, so do I consider that native? That is a native language where we happen to view the virtual machine as a target. Now, this is one of those places which shows you've got a knob, right? You can still opt for, JIT compilation, or you're now using a knob, but you're using a language that was not designed with the assumption that it would be delivered that way, that it would be compiled that way in mind. It can do it, but it was designed, and the programming language designer had in mind at all times full control over object layouts, full control over execution, and going straight down to the metal. So even when we do that, we emit that IL instruction stream instead of x86 instructions, but you're not allocating any C++ types as managed types. .NET does not know about the types. They doesn't know about the member variables or anything. You're not allocating them on GC heap because C++ objects cannot tolerate being put on a compacting heap. They might have inside pointers to themselves. They will break. And it does not work in general. So they're still native types, native objects. You're simply emitting a different code gen path. And to the extent that you want to call that interesting, yes, you can do it. But at some point you question, like, what exactly are we trying to accomplish? If you want the full VM and the always on or default on GC and metadata and VM and that kind of thing, managed languages are designed with that in mind and will help you. Why not work with the tool instead of trying to defeat it and push it into a corner that it really might not have been intended for, even if it may work?
Okay, I think we should stop there. It's 4 o'clock. Thank you, Herb, Alexei, Robert, Walter, for a stimulating discussion.